So this lecture is going to be a little bit about diffraction contrast. And you'll recall from Nestor's talk this morning about the various ways that we can image using these various detectors in TEM and STEM. And this was the mass thickness business. And then we said, okay, what we can do is do diffraction contrast, which means we can set up these two beam conditions deliberately. And then, for example, we might use a 200 reflection, and so it's diffraction by the 200 planes that's giving rise to the contrast. And so if it's happened differentially across the sample, then we're going to pick up some contrast from whatever we're studying. We talked about this. As S is varied, we lose information, and there's more dynamical scattering over here, and you now know why. We talked about it, right? Our dear block waves that are interacting, and we lose block wave 1 as we go to thicker samples, or if we actually deviate from Bragg. So this is the way to set up either bright field imaging. This would be for G plus G, and this would be in this particular orientation. This would be rise to a strong beam here and a weak beam for the minus G. And if you just took that minus G and put it into the middle here, then we end up with a strong G dark field minus G beam. And as we said here, if we actually just brought this guy in, so that's now here, it turns out to be weak, and it's 3G that's at the Bragg condition, and you can work that out by just taking, look, there's 3G there, and hence it's at the diffracting condition. Okay. And incidentally, that's a large deviation there from the 0, 0, 0, and so the image is highly kinematical and not dynamical. We talked about stacking faults and their contrast, and this phase change 2 pi g dot r. We already had that, you recall, so a number of these things, right? So these are our important values of g dot r. Okay, so 0, a fraction, integer and a half. So 2 pi g dot r is 0. This is displacement perpendicular to g. There's no discontinuity in the diffracting planes, and so there's no contrast. And 2 pi g dot r is 2 pi n. Under these conditions, the component of r is an integral number of interplanar spacings. No contrast. And so then we say, okay, 2 pi g dot r is fractional, and then we're going to end up with our diffracting planes are discontinuous, and we're going to pick up some contrast. And there's a set of fringes, showing you this, and we interpreted this in terms of what was happening to the Bloch waves here and in the dark field. And I will remind you, symmetrical in the bright field, asymmetrical in the dark field. And of course we can tell what the intersection of the foil is with the top surface, and we know that that's above background there, and that's above background there, so that is the intersection with the top. So we know the sense of inclination of the fault, and that's the important thing there that we need to know. So the sign of the outermost fringe is important, and these are our rules. So bright field, dark field imaging, the bright field fringes are symmetrical, the dark field are asymmetrical. At the intersection of the fault with the top surface of the crystal, the bright field, dark field is similar contrast, and the intersection of the fault with the bottom, then it's complementary. So these are what we call rules that are always fixed, always occurring. So you can tell at the intersection, and I just say that's because we want to know if it's like this or it's like that. So it tells us what that is. And we make values of 2 pi g dot r as close to 0 as possible. So 4/3 pi is the same as pi over 3. 2/3 pi would be the same as minus pi over 3. So addition to the pi makes no difference. So rules continue. So for g dot r is a third, the bright outermost fringe will occur. For g dot r is minus a third, the dark outermost fringe will be there. So if we assume r is a 6, 1, 1, 2, Then for G is 002, G dot R will be 2/3, and for 1 bar 1 1, it'll be 1/3. And so we normally know exactly what our G vectors are, of course. And our central fringe dies away as the thickness increases, and we know why that is, because that's to do with what's happening with our block waves. And so we must know the actual sign of G. So we can't just say it's either bar 1 1 1 or 1 bar 1 bar 1. We actually have to know which it is. And then that gives us the correct sign for 2 pi G dot R. And you saw that image. So this is bright field and dark field under two different conditions. And there's the reason why. And you'll recall it's just what's happening here in terms of anomalous absorption of one of the block waves, block wave 1. Wunderbar. And you saw that. So we've done this. And how we set up the problem. And you'll be able to read this before you go to sleep tonight if you get hold of the PDF versions. Anyway, so. All right. So on all of this you had this morning. So it was just to recall if I was giving this on 2 different days. Okay, so that's exponential, and that is exactly what's happening here, is the effective CG term. And C naught is not affected by that. Okay, and so we get the asymmetrical profiles. Okay, and this is all from this morning. It's still the same. See if you recall these. Right, so they're using these computer programs to calculate the image profiles. We can manipulate these in these ways mathematically. So the first term is perfect crystal. The second term is independent of the position of the fault. Right, and the third is dependent on T prime, which is where it will show the thickness fringes. Okay, so faults in FCC, intrinsic faults, like 1/3, 1 1 1. That's if we have a agglomeration of vacancies and they collapse into a Frank loop. And extrinsic would be a third, also 1 1 1, and these will be interstitials, and these would be opposite sign, once we know what the particular 1 1 1 it is. And these are bound by Frank dislocations, these faults. Excuse me. If you form a fault by glide, and it's a 16112, and we know there's the Shockley partials that bound that fault. And since 1/3 111 will equal a 6112 and a half 110, then we can unfault our intrinsics. They only differ by a lattice vector, so the contrast will be the same if they lie in 111 planes, since G dot R is an integer or 0 for a lattice vector. Okay. So intrinsic faults. So what we need to know then is how to define the sign of our fault vector here. And so this is defined by the sense of motion of the bottom half of the crystal to make the defect. So in this particular case here, right, so this would move that way, and the bottom half would move that way. So the fault vector defined by the sense of the motion of the bottom half of the crystal to make the defect. So G equals 1/3, bright outermost fringe. G equals minus 1/3 is a dark outermost fringe. So if G is 1 3 bar 1, and R is a third bar 1 1 1, then G dot R is a third. So experimentally, we record the image at S is equals 0. Why? Because with these faults, it maximizes the contrast, both in bright field and dark field. We reverse the sign of G and repeat the dark field and bright field imaging. And then we determine the intersection with the top of the foil, and so we know what the inclination of the fault is. So let's say this is our fault vector, 1 1 bar 1 here. There are images there, and here's our diffraction pattern. So let's analyze these. Okay, so the contrast that you're seeing here has been degraded by the fact it's come from a negative, been scanned in, it's been produced here, it's been projected. So I've taken on the nicer images, I've done a profile here so you can see that. Okay, so that would be the profile from A, and that from B. So B, you can see, has outermost fringe is bright. This guy here. And the outermost fringe would be dark. And C is then dark field, so it's going to be asymmetrical. And D is dark field as well, and that should be asymmetrical. And it sort of is. It comes down here and up there. So for A, the bright outermost fringe is dark. And so if R is a third 1, 1 bar 1, as we suggested, then G dot R is 4/3, and that's equivalent to 1/3. So the bright outermost fringe would be the wrong answer. So therefore R is 1/3 bar 1, bar 1, 1 in that case. And so the fault is actually extrinsic in nature. So we're able to tell something about the nature of the fault from that. This is a sort of 4 faults in silicon. We have A, B, C, D I've marked on there. And A looks like that. B looks like that in terms of... So for fault A, don't you yet. It's either plus or minus 1/3 bar 1, 1, 1. So if we assume it's 1/3 bar 1, 1, 1, then G dot R is a third, so it should be a bright outermost fringe. And that's consistent with the experimental observation. Let's go back here. So A, you can actually see it here, that it's a bright outermost fringe here and here. So, so it should be a bright outermost fringe, we say it is, and so therefore this is, then it's consistent with, if we look at the stereogram, right, for this being direction, a fault vector of 1/3 bar 1, 1, 1 is an upwardly facing normal, and so the fault must be intrinsic. And in fact, I marked that on there. This is an intrinsic fault here. Okay, so for fault B, you can see my bars have moved over, so it's 1/3 bar 1, bar 1, whereas for that orientation. So we assume it's a 1/3 bar 1, bar 1, 1. So G dot R then is minus 5/3, which is the same as minus 2/3, which is the same as a third. So that should be a bright outermost fringe. And we say this is not consistent with the experimental image. And because it's dark outermost fringe, so, and hence this, or that, in actual fact, should be the vector. And so, again, if we look at the stereogram, for this being direction, the 1/3, 1, 1 bar 1 is a downward facing normal, such that the fault must be extrinsic. So we have an intrinsic, an extrinsic, and for fault C and D, we have a 1/3, plus or minus 1/3, bar 1, 1, 1, G dot R is minus 1, and for RD, for the D fault, 1/3, 1, 1, 1, 1, 1, G dot R is 1. So these faults should be invisible. So why can you see them? Right, we have integers for the G dot R's, so why are they visible? So we'll take a look and see the scan looks like that. It's kind of interesting. And D looks like that. So sort of not normal looking kind of faults, right? Not symmetrical in any way, or so why do you think you're seeing them? So what we're assuming is we have a particular fault vector, And so what we have here is an incomplete fault vector, and so we have a supplementary displacement here because of the bonding in silicon. And so why do we see contrast? Contrast due to the presence of supplemental displacements. The hard-seal model is not sufficiently exact. So by doing these diffraction contrast experiments carefully, you can tell quite a lot about your defects. I mean, here we've discovered that in fact, where there should be no displacement at all, there's a supplementary displacement. And that's something to know about your sample. So there are other planar defects that you might see, the pi fringes. This is the case for G dot R is 1/2. And so alpha is pi. So images with S equals 0. Again, so images for S not equal to 0 are complicated. So when the S is 0, bright field and dark field images for a given G are complementary. Bright field, the central fringe is bright. Dark field, the central fringe is dark. And fringe spacing is the extinction distance divided by 2. The intensity of the outermost fringe is determined by the foil thickness. So in bright field, the outermost fringe is dark if the thickness is n times the extinction distance. Dark field, the outermost fringe is bright if the thickness is n plus 1/2 times the extinction distance, where n is an integer. So a little complicated. New fringes associated with an increase in thickness are formed at the intersection of the fault with the fault surfaces. So they actually work very differently from the faults we've been discussing. So consider an APB in a B2 structure. R would be a 1/2 No contrast is observed when imaging with a fundamental reflection. So let R equals a 1/2 then when G equals 110, G dot R equals 1, we have no contrast, and when it's 1/10, G dot R equals 0, we have no contrast. And when imaging with a superlattice reflection, so if R is a 1/2, then if it's G equals 100, we get G dot R is a 1/2, so pi fringes. And if G equals 1/1, G dot R is 3/2, which is the same as 1/2, we'll see pi fringes in the stuff. I didn't have an example to show that, except for found this in APB faults in titania, and you can look at these and see something about the rather complicated contrast here for pi fringes. Delta fringes. These are weak fringes caused by supplementary displacement, as we saw in the faults with silicon. And this is for APB faults in gallium arsenide. And these APBs are inversion domain boundaries, so 180-degree rotation of one part of the lattice with respect to the other. And the translation is caused by the difference in bond lengths between gallium and arsenic. So it's not a lattice translational vector. And by image matching, computer-based experiment has determined that the displacement vector was 0.19 angstroms, normal to the fault plane. So you can still get some information that might be very interesting to you if you're studying this material. Again, by carefully imaging in a sort of controlled manner here to get these image conditions set up correctly. Okay. So back to this to remind us that we can get a number of different diffraction vectors in each of these zone axes. So two beam conditions. We recall that we can go for strong bright field, strong beam dark field, and we can go for setting up the 3G condition for weak beam dark field imaging. So let's think about displacements about a dislocation. So there's a nice edge dislocation. And we'd say, let's say you have the diffracting planes as I've shown. The Burgers vector here is looking like this. And so the major shear around that edge dislocation is parallel to the Burgers vector. And there is another contribution, and that is this B cross U term, which are displacements like this around here. And in a screw dislocation, we don't have that. We just have the displacements parallel to the Burgers vector. So that's just a general view here that we have the Burgers vector and then this B cross U term contribution. And the screw will be much more simple than that. It's just parallel to the Burgers vector. So, of course, if we have a dislocation, then we have continuous displacement fields. And so at some distance from the dislocation, we'll pick up some information here, some distance from it. So, again, the bottom expression there is for a screw, just got the Burgers vector. And the effective displacement looks like that in terms of distance from the dislocation. So obviously there's a lot of displacement very close to the dislocation, but as you go away from it, it decreases. So, and the displacement of the lattice, right, so which is going to affect our diffracting condition, then is given by this expression here. Okay. So this is the effective displacement on the local S value. Okay, it's a kind of complicated diagram, but we have the Ewell sphere there. We have the end of our diffraction vector is here, and then this is now being pushed out to here by the displacement around the dislocation. So contrast from screws and edges at S equals 0. Let's take a look. So this is the calculation for a screw dislocation. So it's computed. We've got solid line is bright field. The broken line is the dark field image. And so you're going to have both cases, you're going to have a dark image here. This is G dot B is 1, and we have a 0.1 for the anomalous absorption here. Okay, so that would be for a screw. For an edge, it's going to look like this. And again, same thing. Bright field image is the solid line, and the dashed line is the dark field. G dot B is 1. So for both edges and screws, we'd say that G dot B equals 1 is going to give us a single dark image, which is, of course, this contrast intensity decreasing here around the dislocation. So contrast from dislocations, S is got a larger value. It's deviated from Bragg. So here it's what have they got here? Where G dot B is 1, and our dimensionless deviation parameter is 0.3, and we still have a dark image here. But interestingly, we have on the one side of the dislocation a higher background here compared with this side. So we'll need to think about that in a minute. So here are dislocations. Nice image. Right, this is silicon iron. And what you should notice is that, right, we have the dislocation lines, that's good. But why have we got a darker gray there and a lighter gray there? Darker gray there and a lighter gray there. Darker gray there, lighter gray there. Why is that? And that is simply because if you note this dislocation, for example, here comes around and back, and around there and back, and around there, and this one comes back. So this is just simply that you have on the one side this, and then if I mirror that, it'll be below background, or it will be above background if there's another dislocation here. So these are just dislocation dipoles here, right? So they're just switched. And so the below background here would be this one with another dislocation here, and the above background here between these two would be this side here, and one mirrored, and then the high background intensity. So immediately you would say those are dislocation dipoles, and you'd be correct. Contrast from segments near foil surfaces. Okay, so all of these really squiggly bits here are steeply inclined to the foil, and when they get near the surface, you really pick up the information right near the surface, close to the surface. So if you're a lonely dislocation in a thin foil, when you get close to the surface, you have image forces that are waking you up like that. And then when you're inclined to the surface, of course, you get a lot of the dynamical effects then that are giving rise to the fringes. Remember where the fringes come from. They come from our Bloch waves. And so if you sit down with the notes, you can work your way through each of these to work out what's happening as you get closer to the surface. So one, if I get back and read this properly. Yeah, 1, 2, and 3 refer to different positions, right? Y over sigma g, right, with respect to the foil surface. And so, again, all that's really happening is our dislocation is in the middle of the foil, it's heading towards the surface, and then it abruptly gets caught up with the image force and scoots up towards the surface, and then we get this oscillatory effect. All right, contrast from dislocations with G dot B is 0. All right. So these are loops here. And this says we have, these are dislocation loops in zinc. We're imaging with a G such that G dot B is 0. Okay, so there's our displacement for these dislocations, that it's a component V and B cross U, so they're edge dislocations, edge loops. And so what are we seeing here? We're seeing a double image here, a double image here, and then almost nothing here. So what is that telling us? So we said we're imaging with G dot B as 0, right? So we think this all should be out of contrast. And the only place it's really out of contrast is here and here. So what we're seeing is that this B term here is out of contrast all the way around. This lot is a contrast from B cross U. And this lot here and here, the G dot B is out of contrast, and the G dot B cross U is out of contrast as well. But so these are just basically residual images here, because it's giving the information is coming from the B cross U term. But this is exactly where both the G dot B and the G dot B cross U are equal to 0. So we know that this is basically a G dot B 0 type image here for an edge dislocation, which is good. We know that. And so these are calculations of exactly that, what you can see. And so these are just computed for that. The M here is G dot B cross U divided by 8, and then they have different values for the M. Okay. But this is a very characteristic image that we'll see shortly in other cases. Okay, so again, dislocation loops here, and these are the calculations of what these should look like. And we have, of course, if you imagine this is now mirrored on the other side, we're going to have two of these, one over here and one over here. So as soon as you see this image here, you know that G dot B is 0 and G dot B cross U is 0 here and here, but not here. So it's a very characteristic image. Very immediately you can say, "Oops," say something. And these are more up-to-date, not very well projected here, images, but it's actually calculations where you can now see what we call the double dotted contrast here, which tells us that we have a G dot B 0 case where we have some residual contrast. Okay. How about contrast from dislocations with G dot B is 2? Let me just remind you that clearly we have a double image here, right? Double image here. And that's because that's where the G dot B cross U contrast is, non-zero. So this is now, but for the rest of the loop, it's G dot B is 0. This is G dot B is 2. And what we have is, on either side of the 0 here, as we go away from the center part of the defect, we end up with these 2 dark images here. Here's the background. So we've got 2 images there, and this is now, this is at G dot B is 2 with at the Bragg condition W equals 0, and this is dimensionless parameter, deviation parameter 0.3 here, so we've gone away from the 0 Bragg. So here we get a dark image and far less of a dark image there. So as we deviate from the Bragg condition, we're losing this part here, and it comes mainly to a single image. So then people will say, if I get a double image from G dot B cross U not being 0, and I get a double image when G dot B is 2, how do I tell the difference? And the way you tell the difference is that you will deviate from Bragg, and in this case, you'll wash out the one side here and go to a single image. In the other case, it'll just get weaker and weaker and weaker, but you always have the 2 images there. So you'll be able to tell very clearly if it's G dot B is 2 or if it's G dot B is 0. Okay, contrast some loops and dipoles. All right. So let's have a look at this. So we have here an extra plane here, shoved in here. So that's an extrinsic fault. Here we have an intrinsic fault. This is inclined like that, that is inclined like that. This is now the same inclination here, same inclination there, but if you look here, this is the G vector here for this case, and this is the G vector here for that case. So let's have a look at this carefully. These little twisty signs here are when the beam comes down and it sees this here, what it's seeing is that that's happening to the plane. That's the twist that's happening to the plane. And here, that's happening that way around. And if we look at the G vector here, anything that looks like an anti-clockwise thing is going to push this G vector into the Avol sphere. And then we'll get diffraction. So I'm looking for then anything that does that. So that would give rise to the diffraction. And that would give rise to the diffraction. That would give rise to the diffraction. And this would give rise to the diffraction. So I'm going to get information from there, and that would be outside contrast. And I get it from there, and that would be outside contrast. So both these cases, where we have the extrinsic fault is like that, the intrinsic one is like that, we'll get outside contrast for this particular value of G dot B. Over here, what I'm going to do is anything that gives me a clockwise tilt, rotation, will push the G vector into the Evol sphere, and I'll get rise to diffraction. And so anything, I'm looking for this then to occur here. So this would be the clockwise rotation. So if we look, here's the rotations here. So clockwise would look like this and this over here, and those would be that and that. So those will give rise to inside contrast, and likewise here we're going to end up with inside contrast. So we have basically a sort of set of rules here that if we know the sense of inclination of the fault, then we have G dot B is positive. G dot B S will be, let me show you this. Okay, so the dislocation position depends on the sign of G dot B S, and these are G dot B S is greater than 0. We have outside contrast. G dot B S is negative. Then we have inside contrast. So these are rules that we can, if you spend some time looking at that, you'll see that that is the case. That we have the inside and outside contrast. These are a set of dislocation dipoles in copper. And you can see it's imaged with G or minus G. And here the separation is small, and here the separation is large. So you can immediately tell that that's a dipole because we've got plus minus G. And if those were parallel dislocations, then it would just be a shift of the image, and they would be the same width. Width wouldn't change. But the width changes if it's a dipole, because they move in the opposite directions. So, contrast some loops then. We say that this is the relative idea. That there are positions depending on the values of your beam direction, your plus minus B, and whether you have inverted contrast. So you want to be in this area here, but that almost only occurs in very few cases. So if we want to say, right, what is the nature of a loop? Is it intrinsic or extrinsic? Then we're going to look at the inside-outside contrast. So the first thing is we're going to determine the Burgers vector. So these two images, you can see you have dark contrast all the way around this loop. So that's not out of contrast. Here, it looks a bit like we're losing contrast there. And I've got another one down here, 2 bar 1 1 here, and you clearly have this thing. So this is the G dot B cross U term. So this is basically out of contrast. G dot B is out of contrast, so we can tell that our Burgers vector is plus or minus a half bar 1 1. And so we'd like to know what that is then. So we do the inside-outside experiments. So that means we do bar 200, 200, bar 1 bar 10, and 110, and then O bar 20 and O 20. So each one of these are pairs. And we will look at the eeks. Oh, I've just done you can see the inside and outside. So with bar 200 we have outside contrast, 20 we have inside contrast for those loops. For bar 1 bar 10 we have, it's very difficult to see, but you might say it's just about outside there and outside there. So these are real examples. So again, outside there and outside there. So outside contrast of bar 200, O bar 20, and bar 1 bar 10. Outside contrast for that. So for bar 200, and assume that we have half bar 1 bar 1. And note that for S is greater than 0 for these images, right? That S is greater than 0. So our G dot B S is above 0, is positive. And so these loops are interstitial in nature. So to see that, if you're interested in really seeing that, let me go back here. We go from here, where we define what we're getting in terms of outside and inside contrast. What you've got to notice is that this is naughty. The version I had before had the Burgers vectors marked on here, but okay. But what we have here is the Burgers. There they are. Burgers vector is up in this direction, and Burgers vector is in that direction. For these up in this direction and down in that direction, and so that's how you then come to know that when I go forward now, and I first determine the Burgers vector. And then from the information here, from these inside and outside, so, and then I make my assumption that it's a half bar 1, and we know that S is above 0, greater than 0, so for these images, G dot B S is greater than 0, and from that then, because we know what the sense of the Burgers vector is, it's headed upwards, rather than not downwards, and so these are interstitial in nature. So that's the kind of information that you can get by doing quite simple plus minus G experiments, and then determining whether the contrast is outside contrast or inside contrast. Okay, so this was the G O bar 2 O in this bar 1 O2 beam direction. And okay, so what this is saying is that we're in this clear thing with a half bar 1 1 and a half bar 1 1. So just to check that we're not running into some inverted contrast situation. Okay, contrast from partial dislocations then. So kind of interesting. So you can see here we have a dislocation on one side here. We have fringes, and then we don't seem to see anything here. Nothing there, some fringes, and then obviously a defect there, a defect there. So it's kind of missing a defect on most of these, around here and here. So what's happening? Why are we missing a defect? And if you calculate what these things should look like, then you essentially, anything with G dot B is a third or minus a third, unless it's essentially it's essentially invisible. And that's what is here. There is a defect there, it's just that it's not visible in the contrast. Whereas on the other side, they're clearly visible here. Okay. And so that's the particular setup there. And you can show that these things are rings. This is of course, the two Shockley partials in that case. So for G equals 1 bar 1 1, and G dot B is about 2/3 and 1/3. The 1/3 will be invisible, the 2/3 will be visible, and that's why we're seeing what we're seeing. This is copper, and this is Ni3Al at the bottom there. There's the diffraction pattern for C and B. Bless you. And then here we have a 2,2O G vector here and a 2 bar 2O vector there. And so let's now just have a look at Berger's vector determination. And what we have here are, we're going to concentrate on these defects here. Let me go back here. So those two here, say to start with, and if you look at O bar 2O, they're no longer visible. So we'd have to say this is going to be a G dot B 0 condition, this is going to be a G dot not 0 condition. You can see that they're back here, those two, and they're here in that condition there. They're out of contrast here again, and in fact they're out of contrast here. So we can build this table up here. The B dislocations, why aren't we marking them? Hold on. Okay, so these are the A's here, and the B dislocations are, I chose a, well, for some reason I haven't marked them on here, the B's. But so just take a look at the A dislocations. Oh, there they are. There's the B dislocations, it's here. So as we go down these various vectors, the 110 G vector, which is this guy here, A and B are both in. 1 bar 10, Berger's vector is 1 bar 10 is this one here. So A is in, and that's in. Okay, don't give up yet. O bar 2O here. This is out, and that is in. Then the 200 is here. This is in, and B is out. And O bar 11, which is here. Then we have our A is out, our B is in. And for bar 101, here, this G vector, then we have A is in, and B is out. And so from this, these BA has to be 100, it's Berger's vector, and B has to be 010. Sorry, no, 010. And essentially, if you have two outs in any given analysis, then you can uniquely define the Berger's vector, the direction of the Berger's vector. Now this is the NIAL B2 compound that these were taken in. And so these are sort of interesting Berger's vectors. This was a single crystal of the B2 compound that was deformed at 600 degrees centigrade. And if these are the active dislocations, if they're gliding, then what it tells us is that we're not going to be satisfying von Mises' criterion, and this stuff should be brittle. But it's not. So it leads us to realize, or to think carefully, that there's probably some climb going on here and not just glide. And so we can, because these single crystals are quite ductile, and particularly at 600 degrees C. But that's how we do this, and of course now we can also do the trace analysis of to find out what the crystallographic analysis, to find out what the directions are. And when you do that, you'll find out that these are edge dislocations. So it makes you even more suspicious that they're climbing. Okay, contrast from particles and small strain centers. Then, so this is intensity contrast from a simulated image of a particle. And notice the line of no contrast here, which corresponds to the plane that is not distorted by the strain field of the particle. So it's very clear, a very distinct image there. And you can calculate it, and the line of no contrast is basically along here in terms of the distortions around this particle. And depending on that, where you are in the relative to the top or the bottom surface, this is how the contrast varies for dark field then on the left and bright field on the right. And so this is a series then, these are all calculated images of course, and therefore different geometries of the A's and the size of the Berger's vector, and then G, the two different G's. And so you can get, by using image analysis, you can then define exactly what you have in terms of your particle. And then weak beam dark field imaging, right? So we said, right, the refracted intensity is given by this, and so this is the effective deviation parameter here. You've seen those terms before. So the refracted intensity decreases very rapidly with increasing values of the deviation parameter. Okay, so this is our effective extinction distance here. Depends on our deviation parameter, or we can write it like that. And so our image widths as well are proportional to this effective extinction distance divided by 3, right? Where that's our effective extinction distance. So if we want very fine images, we need to operate at large deviations from Bragg. But the problem is, in bright field, remember the rocking curve here? In bright field, if we go a large deviation from Bragg, we get to a situation where we have very small intensities. So that's not very useful for us. So what we want is, right, the dislocation image will be very thin, which is great, but also very low contrast. And what we want to do is get something that's very high contrast if we can. So in dark field, at large deviations from Bragg, the images will be thin, but the contrast will be very significant. So if you're in dark field, so a bright image on a very dark background. So if our background is very dark at this large deviation, then any information we have from any diffraction from the dislocation will give rise to then a bright image in dark field. So, and this is very kinematical scattering because it's a very large scattering event. So an example would be if our extinction distance is 40 nanometers and our deviation parameter is, say, 0.2 nanometers to minus 1, then our effective extinction distance is 5 nanometers. And the image width would be about 15 angstroms compared with 130 angstroms in normal bright field imaging. So if you want to pick up, say, a fairly closely spaced couple of Shockley partials, then you're going to use weak beam dark field, because then that gives you a chance to see them rather than not see them because of our relatively large image in normal bright field imaging. So in dark field, at large deviations from Bragg, the image will be thin, but the contrast will be quite significant. So bright image on a very dark background. And so the origin of the contrast, we call R is included in the dynamical theory in that way, that term. Hence contrast arises from a local change in S caused by the displacement field of the defect. And when this equals 0, this term, S plus G dot dr by dz, then the crystal is at the Bragg condition, and there is strong coupling between the bright field and dark field beams. So when we have it, this term is very large, then the crystal is far from the Bragg condition, and diffraction will occur only when there is sufficient bending to bring the crystal planes into the Bragg condition. So it's very close to the core of a dislocation. That's why it's such a thin image. So determining the value of S, if you need to do that, we draw a line through the G systematic row and let the eval sphere cut through this line at NG, where n is not an integer. So what's the value of n? And then you can note, this is an interesting diagram. I think your eyes will start goggling a bit when you look at this. So G, 2G, 3G, 4G, 5G, and then up here we have 3G, bar 3G, bar 2G, bar G, G, 2G, and so on. And so it shows the positions of the Kikuchi lines for the systematic rows, the reflections when 4G is excited. So 4G is excited, so that's 4G is lined up, but then you can see the rest of these start deviating. And so we say that the 3G here will actually end up on 3.5G. So from that we deduce that n is 2m minus big N, so ng is n is an integer, refers to the Kikuchi line closest to the ng, the eval sphere intersection, and mg is the location of the Kikuchi line as measured. And so you can then determine then from that what you need in terms of determining what the S is. So using n equals 2m minus n, and the example shown in the figure, then n equals 3 and m equals 3.1 and n equals 3.2. And so if n is 4, then m is 3.6, measuring the value for the 4G Kikuchi line, and so n is 3.2. And so then S is just given by this equation here, and so values of S for various KVs is shown here. So why would you need to measure the value of S? It's because if you're doing computer simulations of your images, then you need to have that well defined. And that's how you'd go about doing it. And setting up weak beam images, as we said before, here, what you'll do is you will set up your G strong beam bright field here, and then you'll swing this beam into the center. So here it is. It'll be very weak, but in doing so, it sets up 3G at the Bragg condition, and then we view that in dark field. So what you do then is you set up a normal, nice strong beam condition, and then swing that strong beam into the center by tilting the beam, and then you'll automatically then end up exciting 3G and view that in dark field, i.e. with an aperture. And so this is the formalization of it. Okay. So there you can see that the eval sphere is cutting right through the 3G situation there. And typical weak beam images might look like this. So strong beam on the bottom here, weak beam on the top. And you can get very interesting sets of images here operating in the weak beam dark field condition. So this is a 50 nanometer, 500 angstroms scale mark here. So these are clearly quite thin images. Okay, and that will do it for today.